Okay, so this is another lecture on algebraic number theory. We're almost done finishing up the preliminaries from commutative algebra section of Milne's notes, and today we're going to start the review of tensor products section. This lecture will be a little bit longer than the other ones just because there's significantly more material to cover when it comes to tensor products. Okay, so first I'm going to give you essentially the definition of what a tensor product of two modules are. Okay. To do this, first you need to know what a bilinear map of modules are. So I'm going to let M, N, and P be A modules for a commutative ring A. A map. Okay. So let's say I have a map from the Cartesian product. So this is just the set of pairs where the left element is an M and the right element is an N. A map from the Cartesian product of these two modules to this module P is said to be A bilinear. Okay. If for any A and A, M and M prime, and M, and N and N prime, and N, we have essentially, three equalities between all of these things. So essentially it's additive in the first factor, okay, so I can split the function over the addition in the first factor. I can split the function over addition in the second factor. Okay. And it's essentially A-linear in, I guess the short way of saying that, the short way of defining bilinear is saying it's A-linear in both terms, the first and the second factor here. Writing it out formally, it looks something like this. Okay, it's additive in both factors, and I can pull scalar multiples out of both the first and the second factor. Okay, so in short, a map from the Cartesian product M cross N to P is A bilinear if it's A-linear in both factors. Okay. So now that we know what an A bilinear map is, I guess maybe if you've never seen this concept before, the quintessential example is like when A is a field, M, N are vector spaces, and P is the ground field. Then these bilinear maps, a quintessential example of such a bilinear map is like an inner product on your vector space. So like the dot product is probably the first bilinear map that you would encounter. The way we define a tensor product, so a tensor product is going to be a pair QF. Here Q is an A module. And F is a map from the Cartesian product of M and N here are still A modules. Okay. Q is an A module. F from M cross N to Q is a bilinear map. So we say such a pair is a tensor product of M and N if it satisfies the following universal property. Okay, if for any a bilinear map let's say let's say G from M cross N to some module P, we get a unique map H. I should tell you what kind of map this is. We get a unique A module homomorphism. H from Q to P such that the following diagram commutes. Okay, so the diagram looks like this. Start with M cross N in the upper right. I have this map F, my bilinear map, into my tensor product. This map H is the map that I'm guaranteed to exist, so there exists a unique H and this map G. Okay, so if I start with a map G, a bilinear map G from M cross N to P, then I can fill this triangle, and basically I can build a third side to this triangle over here using the universal property of these tensor products. Okay, so such a pair is a tensor product if it has this universal property. Just like with all things that satisfy universal property, they're unique up to unique isomorphism. I guess at this point we don't know that tensor products of modules exist. It turns out that you can construct them, so I guess maybe let me make a couple of remarks here. So what do so I guess kind of a vague but natural question is, what do tensor products do? Essentially, they're like so kind of like a heuristic of what a tensor product is. The tensor product is the largest. So largest in what sense? Maybe this is a little vague. Is the largest module with a bilinear map. F from N cross N to Q. So what I mean when I say largest is that any other pair of a module and a bilinear map, that map has to factor through Q in some way. Okay, so also say maybe there's like this confusing abusive notation. Technically, a tensor product is a pair of a module and a bilinear map. A lot of times, people and both the mathematical community at large, and which includes me, will refer to just the module as the tensor product. It's kind of a very common abusive notation. Okay. So the tensor product is essentially a big module that every bilinear map from n cross n factors through. There's another natural question is like, how do I construct, like how do I know tensor products exist? Why should there be such an A module that satisfies this universal property? And I'm not going to go through the entire construction. I'll just kind of give you the gist of it. One can construct tensor products as an appropriate quotient of the free module generated by m cross n of the the free A module on the set m cross n. Okay, and then m cross n, essentially once you have the module Q as the quotient of this free module, this is kind of like the canonical tensor product construction, and typically we write m tensor over A with n, and the map F is usually denoted, the map F is denoted by sending a pair mn to what we would call a simple tensor, little m, tensor little m. Okay. And essentially, like if you go through this construction, this map here, this map F is essentially embed m cross n in the in this big free module, and then project down to the quotient. Okay. You don't really need to. I guess the only time the actual construction comes up is under some very specific circumstances. I guess when you're first defining it, and maybe in a couple more complicated proofs. The key, like, every time you're trying to work with a tensor product, you should always try to use this universal property rather than this construction as a free module. Using the universal property tends to be a lot easier and, like, quote unquote more enlightening. It helps you kind of like understand what's going on better. At least that's what I've found. Okay, so let's talk a bit about some of the properties this tensor product has. Okay, so first proposition. Okay. So we have an isomorphism maybe let's just say of abelian groups. You might be able to strengthen this. I haven't thought about it. Of abelian groups for any A modules M, N, and P. The bilinear maps, the A bilinear maps, okay, from M cross N into P are essentially, you can identify these with the regular A linear maps from M cross N to P. From M tensor N to P. Okay, and the map here is defined by sending a homomorphism here to decompose with F to get a bilinear map here. Okay, and the proof is straightforward to show this is, so essentially I guess it's really easy to check that this map is a homomorphism. To check that it's a bijection, you just use essentially the universal property of tensor products. So proof, use the universal property tensor products to check this map is bijective. Okay, so this is probably a really, or like maybe not really, but an easy first exercise that gets you to kind of think about how the universal properties of tensor products work. Okay, so there are various questions about like how does tensor product interact with direct sum and direct product, and the next proposition addresses this, at least in the case of direct sum. So the proposition essentially says that tensor products commute with direct sum. What does this mean exactly? Okay, that is, we have an isomorphism. For A modules, let's say I have a big family of A modules Mi. I runs over some indexing set big I, and let's say Nj, where J also runs over some big indexing set. Okay, if I take the tensor product of these two direct sums, tensor over A, okay, then this is isomorphic to, now I can take just a single big direct sum over I and J of Mi tensor over A and J. Okay, so it's kind of a I guess neat thing. Essentially, tensor product, like one way to say this is that tensor product is bilinear in both factors. So I can take and factor out. Basically, I can bring the sums outside in both instances, and then I get a sum of tensor products rather than a tensor product of summands. Okay. Furthermore, I'll tell you what the map is. The map sends, if I have a sum of elements here, tensor, so it sends a simple tensor. Okay, so I guess, yeah, maybe there's another thing I should say here. Okay, so it sends a simple tensor, a sum of mi's and a sum of nj's, to a sum of simple tensors mi and j. Okay. Before I talk about the proof, I'll make a small remark here. So the construction, so if you work through the construction, tensor product, you will find that as an A module, M cross N over A is generated by the image of M, just the Cartesian product, M cross N under F. Okay, that is generated by simple tensors. Thus, to define a map, so to define a map out of a tensor product, okay, I only really have to tell you what it does to the simple tensors. Okay, I'm not saying that you can just send the simple tensors anywhere. You still have to check that this, essentially it has to define a bilinear map on the Cartesian product after you factor through F. But if I tell you where the simple tensors go, that will tell you where any other element goes. I only have to tell you where the simple tensors go. And remember, the simple tensors are these elements in the image of F. They look like little m cross little n, whereas a general element of the tensor product is going to be a sum of these. Okay. The other thing I'll say is that you should really not use this as your first introduction to tensor products. This is mostly meant to be like a brief refresher if you've already seen tensor products. So, yeah. Okay, so let me go ahead and kind of give you the argument for this in some detail. Proposition proof. So essentially what you do is you use the tensor product, use the universal property, okay, of the let's say mi tensor over A and J to define a map. I'm going to call it Gij from mi tensor over A to J. I'll also remark here that a lot of times people, if it's clear from context, people will just omit the subscript on the tensor. So if you see that, don't be alarmed. It just it means that the author or the speaker thought that this tensor product should be clear what you're taking, which ring you're taking the tensor product over. Okay, so I'm going to define Gij from mi tensor nj to the big direct sum on the left. Okay, and essentially the map again, I don't have to tell you what it does to a simple tensor. It's going to send little m, little n. It's going to send it to, well, mi embeds in this direct sum, let's call that O. Okay. So it embeds here by, in the ith component, it's the identity, but everywhere else it's 0. I'm going to call this embedding var phi sub m of m tensor var c sub n of n. Okay, where var phi sub blank from blank to this big direct sum. Okay, maybe I shouldn't do blank. Where var phi, I'll just tell you what var phi sub m is, and var c sub n will be similarly defined. Var phi sub m from mi, sorry. Var phi sub mi is going to be the natural inclusion into this big direct sum. Sending an element m to I think how I want to say this. The natural inclusion, maybe, which is the identity on, I guess, in the ith component. And 0 outside at every other component. Okay. So you can check that you can define a map from the tensor product in this way. Using the universal property. So you define it from the Cartesian product, check that it's bilinear, and then you'd automatically get a map from the tensor product that behaves in this way. Okay, and then you take the direct sum of these GIJs, and that will be your inverse. Taking the direct sum of these GIJs will give you an inverse to the above map, to the previously defined map. Okay, so you can check just by doing composition in both directions that this actually does define an inverse. Okay, so essentially one of the main remarkable things about the tensor product is that it's actually functorial in the following sense. That essentially I can take the tensor product, not only can I take the tensor product of modules, I can also take the tensor product of maps between modules. Okay, so I'm going to define how you do this. So I'm going to let alpha from m to m prime and beta from n to n prime be A-module homomorphisms. And I'm going to define the tensor product of these two maps. Alpha tensor beta is going to go from m tensor n to m prime tensor m prime and it's going to be defined by alpha tensor beta. It's going to act on a simple tensor, and it's going to be basically what you would hope. I just take the tensor product of the images of these two maps. Okay. So you can check that this actually does define a map on the tensor product using the universal property. Yeah. And so essentially, like in fancy language, this essentially makes the tensor product a bifunctor on the category of A modules for a commutative ring A. Yeah. And another general remark I should make is that you can like create this whole theory in the case when A is not commutative, but you have to be a bit more careful. You have to talk about left and right modules and bimodules, and yeah, you can't just take the tensor product willy-nilly of any two modules anymore. You have to be a bit more careful that the sides match up, essentially. Okay, so the first thing about this tensor product functor that I want to say is that I'll also say that if you aren't familiar with like the language of category theory at all, it's not going to be super relevant. Like it will only be relevant in that I'll make some side remarks throughout the course on how you can kind of like categorify these your understanding of these things, but I'm not going to spend any real time on it. Okay. So if alpha and beta are R modules, and they're both surjective, okay, then so is the tensor product of these maps. Okay. Proof. Okay. So all I really need to do is show that every simple tensor is in the image of this alpha tensor beta map, because the simple tensors generate m prime tensor n prime. So it suffices to show so I'm going to start with the simple tensor, let's say little m prime, tensor little m prime, in this tensor product. And essentially the proof goes exactly as you would expect. So since alpha is surjective, I can take m and m with alpha of m equals m prime, and I can do the same thing for n prime. Okay, I can find a little n. I can find a pre-image of n prime and big N. And then if I apply the tensor product map, I get exactly what I need. Okay. So a lot of times you, when you're working with these tensor products, it helps to try to reduce to basically the case where you're only worried about a simple tensor. There is one mistake that's really easy to make, and I've made it myself a couple times. When you're checking, so to check if a map is surjective, all I need to do is check that every simple tensor is in the image of that map. But to check if a map is injective, it's not quite enough to just check that the image of every simple tensor is non-zero. You have to check that every sum, the image of any non-zero sum of simple tensors is still non-zero. Okay, it can happen where the image of every simple tensor is non-zero, but there's some more complicated tensor that isn't zero in your domain, but becomes 0 after you apply the function. Okay, so there's a warning there. Okay, the next proposition turns out to be vitally important, especially in the field of like homological algebra, or probably like representation theory. Anytime you're trying to study modules, the following proposition gives you one of the foundational properties of this tensor product functor. So proposition. Okay. So if I take an exact sequence, a right exact sequence of R modules, if let's say M F, so M prime to M double prime, let's call this map G. Let's say this is an exact sequence. Exact. Okay, remember that means that so essentially this sequence is going to be exact at two places. One, it's going to be exact here, which means that the image of F is exactly the kernel of G. It's going to be exact here, which means that G is surjective. So it is exact. Then so is... I can apply my tensor product functor essentially. So is this sequence. F tensor IDP M double prime tensor P to 0. Okay, for any A module P. Okay, so essentially, one way to say this is not only does tensor product preserve surjections, but it also preserves right exact sequences. Okay, so in fancy language, we'd say that the tensor product is a right exact functor. So proof. This is a fairly important result, so I'm going to give the proof in some detail here. So first, the above lemma takes care of exactness. So we have to check exactness at two spots. So what do we need to do? We need to check one. We need to check exactness at first we need to check it at M double prime P. It turns out this is just going to be taken care of by the above lemma. Two, we need to check it at M tensor over A P. Okay. So to take care of one real quick, recall. So exactness at 1, this is equivalent to the surjectivity of G tensor IDP. So recall exactness at 1 is equivalent to surjectivity of G tensor IDP. Since both G and IDP are surjective, the above lemma gives us the desired result. So G is surjective because this initial sequence was exact. IDP is surjective because it's the identity map. So G tensor IDP is surjective, and exactness at 1 holds. By the above lemma, G tensor IDP is surjective, and exactness at 1 holds. Okay, so we need to work a little bit harder to get a exactness at 2. So what do we need to show? We need, well, I'm going to break this into 2 pieces. We need basically each containment. We need that the image of this guy is contained in the kernel. G-tensor IDP. Okay, and we also need that the kernel is contained in the image. This part B is going to be a little bit more work. Part A essentially follows from a quick computation. So A, note, so if I do F tensor IDP and then I do G tensor IDP on, let's say, on a simple tensor, so for M prime tensor N, or sorry, P, say I start with something here, we have, so if I do G after F IDP of M prime tensor P, okay, this is essentially G of, so I'm going to apply F to the first one and do nothing to the second one. So this is going to be F of M prime tensor P. Oh, this should be G tensor IDP. Okay, and then it's going to be G of F of M prime tensor P. Again, I do nothing to the second factor and I just apply G to the first factor. Since this initial sequence was exact, the image of F is contained in the kernel of G, so this has to be 0 tensor P, which in the tensor product is the one way of writing the 0 element. So because, I guess there are maybe two facts I'm using here, because the image of F is contained in the kernel of G by the exactness of our initial sequence, and 0 tensor P, so 0 tensor any element is always going to be 0 because it's going to be 0 times 0 tensor P, and then based on the properties of these tensor products, it's going to be bilinear. It's going to be linear in the first factor, so it's going to be 0 times 0 tensor P, which is 0. Okay, so general fact, 0 tensor anything in a tensor product is 0 just kills everything in a tensor product. So part A holds. Okay, to get part B, we have to do a bit more work. Okay, so I'm going to go ahead and I'm going to let D, so let's start part B. I'm going to let D be the module, which is, I guess, maybe one other small remark. It suffices to check that on simple tensors, this composition is 0, because simple tensors generate the whole M prime tensor P, and the images of those simple tensors will generate the image of F. And if every image of a simple tensor is contained in the kernel, then the entire image of F is also contained in the kernel. Okay. So I'm going to let D be the image of F tensor IDP. My goal, remember, is to show that this D is actually equal to the kernel. Okay. Since D is contained in this kernel, I can take the quotient. We have a surjection. Okay. So we get this map pi from M tensor over D M tensor over P with the kernel here, and by the first isomorphism theorem, this is isomorphic to double prime tensor P. Okay, so essentially, if you have containment of submodules like this, when you take a quotient, you automatically get its surjection from your module modulo, the smaller submodule, to your module modulo, the bigger submodule. And essentially, it's what do I want to say here? Yeah, you essentially use the universal property of quotients along with your initial projection from M tensor P to the mod the kernel to get such a map. Okay. So the kernel of this map, the kernel of pi is going to be essentially this guy, cur G tensor IDP plus D as a submodule of this quotient. To show that this map is, to show that this kernel is contained in D, it really suffices to show that pi is injective. Okay, so let's think about this for a minute. If pi were not injective, or maybe the other way around, sorry. If this guy weren't contained in D, then this set here, this submodule of the quotient, would have a non-zero element, which would have to be in the kernel of pi, which would mean that pi is not injective. So if cur G tensor IDP were not contained in D, then this thing would have a non-zero element, cur pi which is this thing, would have a non-zero element. Okay, so it really does suffice to show that pi is injective. And essentially what we're going to do is we're going to define an inverse from this guy back to this quotient here. So define Q from M double prime tensor P to this quotient M tensor P mod D by Q of M double prime tensor P is going to be M tensor P plus D, where M is a chosen preimage, is any preimage of M double prime under G. Okay, that is G of M equals M double prime. So there are a couple of questions like, why is this thing well defined? So I guess first you should check that it doesn't matter which preimage of M double prime I pick. So we see if g of m1 equals m double prime and g of m2 equals m double prime, then the difference of these two guys is going to be in this thing D. It's going to be in the submodule D. It's going to be the image of F, since m1 minus m2 is going to be in the kernel of G, which by hypothesis is also the image of F. Okay, so essentially it doesn't matter which preimage of m double prime I pick. You also need to check that Q, essentially you need to check that Q can actually be defined using the universal property, that this map actually is bilinear when you consider it as a map out of the Cartesian product. And the last thing you'd need to check is that this actually does define an inverse to our map pi, or I guess our map pi after this isomorphism. So one can check that Q is inverse to pi considered as a map to this tensor product. Okay, so this part B is kind of where the magic happens. It's definitely the most challenging portion. Just to give you an overview, essentially you take a quotient by the image, and you really want to show that this quotient by the image and the quotient by the kernel are the same thing. To do this, you define an inverse, and using the fact that our initial sequence was exact, you can show that this inverse is necessarily well defined. Okay, so this is how you prove that the tensor product is a right exact functor. What I mean when I say right exact functor is that when you take this sequence and you apply the tensor product in this way, you necessarily get takes right exact sequences to right exact sequences. Okay, and there are several important corollaries to this. So the first corollary I want to get out, so I'm going to let M be an A module, and this guy be an ideal. I'm going to define the M submodule with coefficients in this ideal A. It's essentially sums AI MI, where AI is in the ideal, MI is in the module. Okay. And then if you want to understand this quotient, one way to do this is it's the same as when you take the quotient ring A mod A and you tensor over A with M. Okay, so maybe it's, I think it's more helpful for me to think about this the other way around. Understanding what a tensor product actually looks like can be hard generally, and understanding this quotient module tends to be a little bit easier for me. Okay, so we're going to essentially consider an exact sequence, so consider the exact sequence of A modules zero. This ideal is going to embed into A, and then I can take the quotient by A mod A to 0. So notice that we've got a right exact sequence here. If I just forget about the first 0 term, I can tensor over A with M and get another right exact sequence. After tensoring with M, so we get this following exact sequence: M tensor A, ID M, tensor I. I should also, maybe this wasn't clear, I should also remark that it doesn't, in the land of commutative rings, it doesn't matter which order you take the tensor product in. So M tensor A and A tensor M are the same thing, and you can be really casual with the order in which you write your tensor products. Okay, and I guess when I say the same thing, I mean canonically isomorphic. I don't mean the same sets. Okay, so I've got this ID M tensor, my embedding I, M tensor A, IDM tensor pi, and this finally ends up in this thing. Okay. So, first thing I want to remark is that if you define, so I'm gonna define a couple maps here, and then I'm gonna leave a couple of things for you to check. So, define Barphy1 from M tensor A to the module A with coefficients in the ideal A. Okay, I'm going to send a little M tensor a little A just to the product AM, and Barphy2 is going to go from M tensor A to big M, and it's basically defined in the exact same way, but this time A can be in a larger set. Then Barphy1 and Barphy2 are both isomorphisms of A modules. So if you want to check that these are actually isomorphisms, I would suggest trying to define some kind of an inverse. Okay. Not only this, we get a commutative diagram, which is really nice. Furthermore, the following diagram commutes. From M tensor A. So the first row is going to be this this row here. Okay, and this second row is essentially going to be a M This is going to be m, and then this is going to be, so this is going to be the inclusion, this is going to be var phi 1, this is going to be var phi 2. Okay. And then essentially what you can do is, using this commutative diagram, I can trace through, starting from here and going up. You can check that that is an exact sequence, and that exact sequence induces an isomorphism from m mod this guy am to m tensor the quotient. So in more words, I'm going to let psi be idm tensor pi composed with var phi 2 inverse. So it's go backwards and then go to the right. So let me go ahead and draw an arrow here. So essentially, this is psi, and it makes that diagram commute. We see that psi from m to this thing is surjective. Okay, since this thing is surjective and var phi 2 inverse is also surjective, the composition is surjective. And not only this, it has kernel. Has the correct kernel. AM. So the way you would check that this has the correct kernel is I'd take something maybe in the kernel here. I'd pull it back up to here. So I'd pull it under var phi 2. I'd see that it maps to 0 under this guy, so I could pull it back to here. Once I've pulled it back to here, I'd push it down and see that these two things essentially match. So essentially, what I want to say here. Maybe I'll actually go through this in detail. So this is one of these diagram chasing arguments, and it can be useful maybe to see it done a couple times. So I'll go ahead and do this in a bit more detail. So first, so what do we need to do? We need to show two things. We need to show that this thing is contained in the kernel, and two, we need to show that the kernel is contained in that guy. Okay. So let's go ahead and try to prove one. I'm going to let so this module is generated by little a times little m's where is in my ideal and m is in the big module. Okay, so I'm starting with a guy here, and I need to show that and I need to show that essentially that psi sends it to 0. Okay, so psi of a dot m. Okay, so just using the definition of what psi is, this is going to be idm tensor pi of var phi 2 inverse of a dot m. Well, var phi 2 inverse of a dot m is going to be a tensor m. Okay, so remember that a tensor m maps to a times m under var phi2, so going backwards, this thing's got to pull back to a tensor m. Okay, so this is going to be, oh, I've somehow swapped my factors here. Sorry about that. Oh, okay, I'm just going to ignore that and pretend these two are swapped. This is going to be m tensor pi of a. Well, since a is in this ideal a, pi of a is 0. So this is m tensor 0, which is 0. Okay. So I didn't even have to use, at this stage, I didn't even have to use the commutativity of this diagram. I actually just had to use the definition of var phi2. Proof 2, I need to show that the kernel of psi is contained in this thing. So I'm going to let's say m be in the kernel of psi. What does this mean? This means that IAD m tensor pi of var phi2 inverse of m equals 0 in this tensor product. Okay. The first thing I'm going to do is, well, var phi2 inverse of m can be just realized as ID m tensor pi of m tensor 1. So remember, again, I just take the product of these two things to get the var phi2 sends a tensor product to the product of those two elements in the module. So when doing that, I'm going to get n tensor 1. Okay. And now at this point, I'm going to use the fact that this sequence is exact. Okay. So since this guy is 0, I can pull this back. So thus m tensor 1 necessarily has to be in the image of IDM tensor this embedding. Okay, so I'm going to go ahead and write it as such. So let m tensor 1, it's going to be a sum of simple tensors here. Let's say mi tensor ai, where ai is in the ideal and mi is in m. Okay, so that's what the image of this map looks like in m tensor a. I guess maybe if I'm being careful, I want to write this as ID m tensor this inclusion. Okay, and now I'm going to apply var phi1 to this thing. I claim yeah, okay, so essentially at this point I need to use the commutativity of this diagram. So note m is going to be, well, it's ID is var phi2 of m tensor 1, which is var phi2 of ID m tensor the inclusion of this thing, mi tensor ai, which now, using the commutativity of this diagram, instead of going around the right, I can go around the left. This is going to be the inclusion of var phi1 of some ai tensor mi tensor ai, which is essentially just going to be the sum of ai times mi, which is in this thing. Okay. So in the second part, the commutativity of this diagram actually plays a key role. So in conclusion, I found that m is necessarily in the module generated by m with coefficients in the ideal A, which was what I desired to show at the beginning. So this shows 2. Okay, so just to wrap it up, what we've shown is that this map psi is surjective from m to this quotient with kernel am by the first isomorphism theorem. We necessarily get this isomorphism. So the isomorphism here follows from the first isomorphism theorem at this point. Okay. There's one last thing I need to say about tensor products. Okay. So essentially, I can take tensor products of modules and or I can take tensor products of algebras and still give them an algebra structure. Okay. But maybe I want to talk about something slightly different here. So I'm going to let B be an algebra. Yeah, I guess really what I want to talk about is something called extension of scalars. Okay. So B is an A algebra and M is an A module. Then B tensor over A with M has a natural B module structure. It is a B module. Okay, with structure determined by the following. B times a simple tensor. Essentially, I just multiply the B's together. B times B prime. Tensor M. Okay, and we call this module, we say B tensor over A with M is the B module obtained from M by extension of scalars. Okay. So like one classic example of this is when you take a real vector space, so like say a 4-dimensional, you take R4, and you can tensor it over R with C, and this is going to give you a complex vector space from your real vector space. This is probably the most classic example of extension of scalars. So we have a natural embedding of my module into the extension of scalars. So we're going to define an embedding M to B tensor over A with M by this thing is going to be 1 tensor M. You can check that this is well defined. And furthermore, this guy's got a universal property. B tensor over A with M I satisfies the following. For any alinear map, alpha from n to n into a B module n, there's a unique bilinear map alpha prime from B tensor A. So from the extension of scalars to n. Okay. This map alpha prime satisfies the condition that alpha prime of this embedding is alpha of the element m. Okay, so what is essentially what is this universal property saying? It's saying that any map from M into a B module factors through the extension of scalars. Okay. Okay. And similarly to the universal property enjoyed by tensor products, I also get an isomorphism of Hom spaces. So the map alpha maps to alpha prime defines an isomorphism. Hom. So the A module homomorphisms from M to N, these are the same as the B module homomorphisms from B tensor A, the extension of scalars of M to N. Okay. And you can prove this in a similar way to how you proved the proposition where this was bilinear maps and this was morphisms from the tensor product. Okay, so this is the last major thing about tensor products. We will use them. They will appear, but they won't be like they're not going to appear every day in these lectures. But you do need to be somewhat familiar with the properties of tensor products. Okay.